So welcome everybody. As they say, all good things must come to an end. So we are approaching the last of the lectures of the 2021 Dirac series. And again, I'm absolutely delighted to introduce a friend and colleague that I've known for a long time, Professor Martin Savage. I already introduced him last time, but I want to make sure that you all know that he's the founder of the incubator program at the University of Washington in Seattle for quantum simulations. And he was just telling me that they already have a full group of student postdocs, so I'm sure it's a very vibrant environment. And Martin, we're delighted to have you, and I'm looking forward to hear about more exciting things that you're doing. So please feel free to share now.
Okay, thank you, Jorge. So, okay. So thank you very much for that really kind introduction again. And I need to do one more thing before I get going here. Okay, there we go. Yeah, thanks very much for that introduction. It's a pleasure to be back for part two. So this time I want to start by saying some words about entanglement and then go into quantum simulation, what's been going on in the field and the vision for where this is going to go. And there's been a number of really kind of interesting, I mean, not just kind of interesting results obtained in the general area of nuclear physics, spanning the breadth. And it started approximately, at least this is when I started to clue in 2015. So this was quite early. There's a paper by Steve Shute considering entanglement and separability in the context of heavy ion collisions. And so his line of argument and reasoning here was one starts with two nuclei, which are pure states, and then in a peripheral collision, there's basically an amputation that occurs, as indicated by the purple oval here, and then there's a mix. Then what's left is a mixed state, and then particles going into the detectors. So these mixed states go down the beamline, and then there's particles going to the detectors. And I'm going to say a little bit more about this in a little bit. There's been also interesting developments in the areas of just what is the entanglement structure of quantum many-body systems and quantum field theories. And of course, on the high energy side of things, there's been decades of effort in understanding entanglement in quantum field theories, ADS, CFT, and so forth. And that is migrated and continues to migrate that knowledge into nuclear physics. There's some really interesting work of a couple of years ago, again in proton-proton collisions by Dirac and Baker on looking at thermal distributions of particles produced in these collisions. One of the things one sees in heavy ion collisions is that thermalization occurs much more rapidly than one would naively guess based on strong interaction timescales. And so the current thinking is that this is rooted actually in entanglement. Then there's discussions, as I mentioned last time, I won't dwell on it again, on fragmentation functions. There's some nice work by Dima related to parton distributions, particularly gluonic parton distributions in the context of entanglement and entanglement entropy. And then there's been some work on nucleon structure, nucleon interactions, and nuclei. So one of the early papers that again was really kind of an eye catcher was in 2017 by Alba Severa Lieta and collaborators in Barcelona. And it's interesting to note now that just recently Alba has returned to Barcelona and heading the Quantum Spain initiative and putting a quantum computer into the Barcelona Supercomputer Center. So they wrote a paper based on perturbative analysis of the standard model, particularly electron scattering and other asymptotic particle scatterings. And they recognized the fact that the couplings in the standard model, in particular, the weak mixing angle being around about 1/4, when looking at the entanglement induced through the scattering of polarized electrons, actually generates maximal entanglement. So the conjecture in here, based on what's known theoretically, that in fact nature is driven, at least in the electroweak sector, towards some underlying principle of maximal entanglement. And so this is pretty interesting, having, the electroweak modeling and model building, having sine squared theta W of 1/4 is something it's not so difficult to achieve in model building, but in this context, in terms of entanglement, it's somewhat of a unique perspective. In the structure of the nucleon, there's also work by Silas Bean, a colleague of mine here in Seattle, and his student Peter Ehlers, who looked at the spin structure of the nucleon in Weinberg's chiral multiplet construction. And what you find if you just write the nucleon wave function in terms of one chiral multiplet, then G axial is 1, and it doesn't describe nature in any precise way. On the other hand, once you add when you have more than one multiplet contributing, with of course unknown coefficients, then in fact even with just 2, one can recover G axial reasonably well, 1.4 as opposed to 1.27. And then one can also fit the quark contribution to the spin of the nucleon phenomenologically. And one finds that the entanglement entropy is of order 1, so it's maximally entangled. So in the context of a hadronic model for the structure of the nucleon, in separating valence and C contributions, one finds in fact also that in this particular modeling, one is driven towards maximal entanglement. So that's pretty interesting, and maybe this is a generic feature of nature in general. And so one of the works that I was involved in with Silas and Natalie Clough and David Kaplan was looking at the 2-nucleon system and asking, does the system also approximate maximal entangling power or maximal entanglement? And the answer is, in fact, it's the exact opposite. If you look at the S matrix, as I've shown here, consider it as an operator for non-relativistic spin systems, then what you find is that you can write it exactly in terms of the phase shifts of the spin 1 and spin 0 channel and spin 1 channel. And then you can ask, what are the relative coefficients of these two different contributions? And one finds that there's an identity piece, which doesn't change the entanglement of initial state between the initial state and final state. And then there's a spin-dot-spin interaction, which does. And nature has chosen the phase shifts in such a way that they're very similar. They're both pi over 2. And even if they weren't similar, near pi over 2, even if they were just the same, exhibiting a spin flavor symmetry, for instance, then in fact, you would be in the situation where the strong interactions between nucleons has minimal impact on the entanglement of the state. It's really driven towards minimally entangling. And so this is the exact opposite. So you have a situation where if you're looking at the electroweak sector and you're looking at perturbative constructions or modeling of the structure of the nucleon versus the interactions of nucleons and nuclei more generally, then in fact you go from the situation of minimal entanglement due to the electroweak sector and strong interactions to minimal entanglement. So there's kind of something that obviously that very interesting happens here with regard to the entanglement structure as you move through confinement in the chiral symmetry breaking scale. There's been a number of other works in this area. One of them has been looking at the production of entanglement between lambda baryons produced in heavy ion collisions. So this was in the context of a hadronic string model, and so one formally in an ideal situation on a perfect quantum computer, one will actually find a signature for violations of Bell's inequalities in the context of looking at the correlations between the spins of the two lambdas produced in the events. When one goes onto a quantum device, however, one finds that the quantum device, its imperfections mask that. And so it's going to require significant advances in quantum computers and quantum devices to actually see the quantum correlations in this hadronic string model for lambda production such collisions. But this is a very nice kind of creative piece of work here, and starting to move, looking at quantum to quantum correlations produced in fragmentation, and this is a non-trivial fragmentation process. Some work that I was also involved in, it was led by Carolyn Robin, also Natalie Pillay, was looking at organizational principles that may become available in considering the entanglement structure of quantum many-body systems. So there's a nice work from 2018 by Gorton and Kelvin Johnson. It was Gorton's master's thesis, where they looked at the entanglement entropy of quite a range of nuclei, and identified systematics and patterns in the entanglement entropy. So if we think about decades old nuclear physics modeling, where there was insufficient computational power and understanding to do these things as we can today, it was very efficient to think about a small number of nucleons as a dynamical Hilbert space based upon an inert core. So for instance, building upon an oxygen 16 core, which would be then tensor producted with, say, 2 nucleons in oxygen 18. And so while we didn't really think about it at the time, this is really, this tensor producting is automatically organizing with regard to entanglement. And so one can return to that thinking today, and we did this starting with chiral interactions and the wave functions that are generated by chiral interactions, and then doing self-consistent inclusion of two-body correlations into the wave functions, and asking how does that change the distribution of entanglement in the nucleus. And particularly we were looking at distillable entanglement, and then mutual information between two particles, and also entanglement entropy. And so the harmonic oscillator base is a particularly nice basis to use because of its analytic structure. And so what's shown here in the middle panel is the negativity, or the upper limit of the distillable entanglement. You can extract between you could potentially extract between two nucleons in a harmonic oscillator basis. And then when you self-consistently and iteratively include two particle correlations, in fact, that new basis, in fact, the negativity goes to 0. So that was pretty interesting. And then if you look at the mutual information on the right panel here, you see that there's interactions and entanglement between multiple single particle levels in the harmonic oscillator basis. And then after including the two particle correlations, one really recovers a very nice core. So the thinking here is, as I mentioned last time, is that essentially you're not going to be in a situation of having an isolated quantum computer. You're going to have a quantum computer embedded in a huge amount of classical computing resource. And so the pieces of the problem that can be done classically should be done classically, and the pieces of the problem that have to be done quantum mechanically can be pushed off to the quantum processor. And so from a multi-body nuclear physics point of view, and computations and nuclei, is by processing as much as possible and understanding the entanglement structure will allow us to then make that separation for hybrid computations going forward. So on the quantum field theory point of view, and I mentioned this last time, in the very far infrared, we have quantum chromodynamics, and which is with relevant degrees of freedom of the quarks and gluons. Massless and nearly massless particles are essentially free. And so then as we move into the infrared, or look at the systems with longer wavelength probes, then the couplings become stronger and stronger logarithmically, and then eventually strong enough where one sees confinement and chiral symmetry breaking. And then as you go off to even longer distances, the strong interactions, if you turned off the pion mass, then you would just have derivative interactions and at zero momentum free fields. So you're in a situation where you go from massless free fields to massless free fields, and this is just an approximation in both instances, but it becomes better and better. So this has led us to spend quite a bit of time understanding entanglement structures of massless or massive non-interactive scalar field theory, as just a way to get some understanding of what the entanglement structure is in such a simple system, or naively simple system. I have to say that some of my colleagues have tormented me for thinking about non-interacting massless scalar field theory. However, hopefully that we've convinced them that it was interesting. So imagine the situation where you have massless non-interacting scalar field theory. And so the vacuum state, the ground state of that, of course, is a pure state. And then you take two regions, you just carve out some approximately circular regions. And then you start asking about the entanglement between those two regions. And because if we work in the massless limit, then there is no intrinsic mass scale. I mean, you have the lattice spacing, and then you have distances given in terms of the lattice spacing, both the size of the system, or the number of pixels in each of the regions, and then the separation between the edges. And again, there's no unique way to form these regions. They're approximately true up to lattice spacing artifacts. And so one of the interesting features of this is that if you ask what is the distillable entanglement in these two regions as you separate them, then you expect to find some function as a function of separation divided by the size. One has to have dimensionless objects with some overall scale. And in each of these correlation functions, the propagator, the scalar field propagator is logarithmic in one dimension, and the correlator between the conjugate momenta of the fields is polynomial. It's 1 over r squared. And as you go to higher dimension, again, you just have polynomial contributions to both correlation functions of the field and also the conjugate momentum, and there's no mixed term. And so if you ask then what is the distillable entanglement between those two regions, you find it's actually falls exponentially in the limit where you take the lattice spacing to 0, and at a finite lattice spacing, you find it follows approximately an exponential. It's got some wiggles in it, and then at some point it abruptly falls to 0. So there's a couple of interesting lessons here. So firstly, from a theory with polynomial and, in the case of 1D, a logarithmic correlation function, you get an exponentially falling function. And so at the moment, there's no known way to analytically compute what the argument of that exponential is. And so we perform these computations numerically in 1, 2, and 3 dimensions. There's a sign problem in this computation, which makes it tricky to go to higher dimension, but we're working on that. And so what you see here is that beyond some separation, relative separation, the distillable entanglement drops to 0 at any finite lattice spacing. And so, instead of following the exponential curve, it just goes identically to 0. So it does tell you that in lattice calculations of quantum field theories, at any finite lattice spacing, if you're looking at regions of the vacuum that are far enough apart, then in fact you get the quantum correlations wrong. Now the question, of course, is how wrong are they? And well, they're exponentially small at at large separations, and these are tiny numbers that you see here on the y-axis. But nonetheless, there is a region you actually don't get the quantum correlations right in any lattice calculation. So there's some interesting lessons there. And if you look at the typical lattice spacings used, not today, but say 10 years ago in lattice QCD calculations and the volumes, then in fact, you were getting the quantum correlations wrong at the largest displacements you could find in those volumes. So it's not entirely an irrelevant exercise. So another interesting thing that comes out of this is if you look at where the support of the wave function is as you increase the distance, as far as entanglement goes, then in fact, as the distance becomes larger and larger, the support of the wave function moves in fact into the ultraviolet. So large distances is actually the entanglement at large distances between separations of these regions is determined by the high momentum behavior of the theory. So with a lattice, of course, one's done horrible violence to the theory just by chopping off the momentum. In general, of course, nature is not going to work like that. There's going to be some smooth transition to a different particle content theory. But nonetheless, what this means is as you go far away and look at the entanglement, if you could measure it, then you would see modifications. You're actually probing high momentum physics, high energy physics, short distance physics, which is somewhat in contrast to what you would think. Typically, you think large distances, low momentum, but in fact, it's not the case for entanglement. So there's a UV-IR connection. On the experimental side, there's some really nice experiments that are being brought up and results being obtained, and you're seeing these now at meetings and conferences. In the last DNP meeting, there was, in fact, of order 10 sessions on quantum information science, and this was one of the presentations there. And so by using Josephson junctions and capacitors and putting them together in clever ways, and here's a figure that I extracted from this paper shown here on the lower right, then in fact, they're able to perform analog simulations of lattice conformal field theories, such as the Massless scalar field theory, as I just talked about, and also the lattice Sine-Gordon model, where in fact one has solitons, non-trivial field configurations. And so these devices are modest to large, in fact. There's devices with thousands of these Josephson junctions. And so I would say stay tuned, because I think that there's going to be interesting results obtained here on looking at these conformal field theories and these lattice Sine-Gordon models from these analog simulations. So moving on to quantum simulation, and just let me try and do a comparison here between what one does in lattice QCD, because that's what I know really, and quantum simulation. And so in lattice QCD, one performs large scale Monte Carlo runs to generate snapshots of the vacuum, and generates typically an ensemble of gauge field configurations that, once you perform statistical averaging over any observable, expect to faithfully reproduce the actual true value of the observable. And so then the method of computation is you take a gauge field configuration and typically will generate quark propagators from one or more, and in many instances all of the lattice sites, and perform one-to-all or all-to-all propagators. And then one ties them together in specific ways to generate the hadrons that one's interested in. So pions, nucleons, multi-nucleon systems. And of course, so then there's uncertainties in these computations because it's a statistical sampling. One has there's well-known ways to perform estimates of the uncertainties from the sampling, and that is actually non-trivial all by itself. There's, of course, systematic errors. You have a finite lattice spacing, you have a finite volume, your tunings are imperfect, and so there's a number of uncertainties that one has to quantify. But the nice thing about that method is that, in fact, it's systematically improvable. On the quantum simulation side, it's very similar. One thing, when simulations of quantum field theory are going to be done with a lot of the technology that's been developed in lattice QCD, and one's going to be thinking about lattice Hamiltonian evolution on a quantum field theory. So one has to prepare initial quantum state. So as I mentioned last time, that's actually a QMA complete problem, typically. And so there's going to be a lot of thinking and understanding in how to actually perform that within the target error bar. Then one applies unitary transformations and operations on that quantum state for time evolution. And then one performs measurements on the register after that evolution and produces strings of zeros and ones if it's qubits. And then again, one is averaging correlation functions, many snapshots. One takes initialize the register, time evolution, measurement, repeat many times. It's a statistical process. And so again, there's the need for understanding statistical uncertainties and the systematic uncertainties, which are now different, but they're not that different. So there's been some just beautiful work in spin systems, and because of the nature of the problems, it's actually easier to explore somewhat larger systems spatially. So here's an example. This is work from this year by Ash Milstead and others at Caltech and Google. And one sees a Hamiltonian, it's a spin system with Z interactions, a coupling times an X operator, and then another coupling, a different coupling to a Z operator. And so initially this just said lambda equals 0. So essentially, so one has the Ising model, and one can, and so this in one dimension supports kinks. And so this calculation was supporting kinks, and then setting these kinks towards each other, and then asking what happens next. And what you see here, the colors show the entanglement entropy when you slice the system, when you slice the one-dimensional system at this particular point. And so you see
Martin,
that as
Martin, let me interrupt you for a sec. So this is just an Ising system. So the Z's are the spin ups and spin down, right?
Yeah.
What are the X's?
Oh, so this is an interaction with an X operator. So this does something else. So there's a background field here.
Okay.
So basically there's a background magnetic fields in the X direction and the Z direction, as well as the ZZ coupling.
Okay, thanks.
And so then what you see is that these kinks move backwards and forwards amongst through each other. The entanglement entropy actually changes every time they pass through each other. So it's not like it's a trivial process. And then eventually it looks like it just sort of washes out. Now, but the important point to note here is there's no inelasticities. Now, on the other hand, when you turn on the coupling, the lambda coupling, then in fact this allows inelasticity, so you can actually have ballistic particle production as these kinks collide. And so this is moving, this is a spin system model that's allowing us to start to move towards inelastic processes, for instance, as you'd like to examine in proton-proton collisions. So there's a lot of technology and understanding of the entanglement, and also just of the process of performing these calculations that we can gain by looking at spin systems. And so this is why there's a lot of activity at the moment in actually simulations of spin systems that are relevant both numerically and also conceptually to what we want to do in the standard model. So I want to give a couple of summary graphs before I move into some more detail here. So the quantum simulations, both on simulators and also on quantum devices, are just starting over the last few years. And here's sort of an incomplete summary of computations that have been done. Excuse me. So the first computation was, this is where my cursor would be great. First computation here was on the right side, second panel down from the top. So this was a computation of the Schrdinger model. It was 4 lattice sites. It was done on a trapped ion system at Innsbruck. And so this was an eye-opener for me, because this was the first time we could actually see particle-antiparticle production in time evolution in a quantum field theory. This is something you can do on a laptop easily. And so from a physics point of view, again, it's not changing what we understand about physics, but this is changing the fact that we now have technology emerging where you can start to move towards doing real-time dynamics of quantum field theories and actually looking at the dynamics of pairs popping out of the vacuum. And so this has been now extended. So there was one-dimensional U1. So this is one-dimensional QED, which shares features with QCD. For instance, charges are screened. The vacuum has a non-trivial condensate. There are 2-body and 3-body bound states in the system. So we can start to think about looking again at fragmentation and even nuclei. Then it doesn't, quantitatively, it doesn't look like nuclei, but it allows us to start modeling in low dimensions. There's been work in issue 2 Yang-Mills, but again, just at the level of 1 and 2 plaquettes, because that's what the devices can handle, and also issue 3. There was a really interesting work in the last year that was different from these. It was done on the D-Wave annealing device, and it actually shows the time dependence of an SU2 plaquette, but accomplished on an annealing device using a really nice algorithm to extract time dependence. So this is something that was somewhat of a surprise to me. Not been really thinking that the annealing devices could give us quantitative information on time dependence, but it looks like clearly that I was just asleep, and it can be done. So on the Schrdinger model in particular, so I've already said pretty much what I want to say, but there's two results coming out of Brookhaven. So these are the lower right and center. And so here you have a one-dimensional system, and you can have a non-zero theta term. So this is an object that looks like E dot B. And so you can prepare the state at, say, theta equals 0, and then you can change theta abruptly and ask, what does the system do? And what the system does is by this abrupt change in theta, then it turns on an electric field in this one-dimensional system, and you start seeing a non-trivial flow of charge. And the system then eventually equilibrates. So the middle panel shows the average value of the vector current versus time after the quench. And then the right panel, again, to do with the theta term, in a classical simulation of such systems with a non-zero value of theta, actually there's a sign problem. And so for large-scale systems, in fact, the classical configurations become exponentially costly. However, that's not the case on a quantum device. One's dealing with a Hamiltonian with real coefficients for the theta term. And so then the question is, how efficient is to find the ground state? And they demonstrated very nicely that you could actually find the ground state in this problem at any value of theta. Now again, these were both done on classical computers, but it points out that conceptually and also, algorithmically, as one goes to scale, one expects to be able to, there will be a system size where the quantum devices will outperform the classical ones. Just check time. Okay. So in issue 2, so this is work that I did with Natalie Clough and Jesse Stryker, and there's also work by Randy Lewis and Raman and collaborators. So here, these were the first calculations of an issue 2 system on a quantum device. We used IBM's Q experience devices. They were the actual problem mapped onto just a small number of qubits. And we took advantage of the fact that in the lattice construction, you have a gauge invariance on each of the lattice sites. And so with real constraints on the coherence of the hardware, it was convenient to integrate over all of the possible alignments, the redundant's not the right word, but all the possible gauge transformations at each of the sites, and reduce the number of qubits in order to perform the simulation. And so what you see here, this result in the middle left panel, is what we could do on the quantum device before the device essentially decohered as a function of time. So one prepares the system in the vacuum, in the trivial vacuum, and then lets the system evolve, and then you'll see gluons, the issue 2 gluons, come in and out of the vacuum. And so that's measured by the expectation value of the electric field. And then in the right panel, this is the work, issue 2, also on IBM's Q experience by Randy Lewis and Christine Mushik and collaborators. And they were able to find the ground state of this one-dimensional system, and also the mass of the lowest lying hadron using variational quantum eigensolver. Basically, this is the hybrid algorithm that I told you about last time, where you have a Bayesian optimization on your classical device and then evaluation of matrix elements with those parameters on the quantum device. And so this was really nice work. You see the precision is good. and it reproduces well what you expect that you could perform on a classical computer. So one of the interesting areas of intersection that's I've been known for decades actually is in the area of error correction, and it's I believe you've already heard about this in detail, so I'm not going to dwell on it. But you know, one of the challenges faced in quantum simulation or quantum sensing or essentially anything quantum is the fact that quantum correlations are fragile, and they are fragile to being disrupted, destroyed by interactions with the environment. And so then, in 25 years ago, more than 25 years ago, there was an amazing period of time where people figured out, Shor, Keneal, Laflamme, Zurich, Aronoff, Benor, Kitaev, Preskel, others, that there was algorithms that could be developed, quantum algorithms to stabilize against stabilize against errors and the destruction of quantum correlations. So one has the Shor code, the Toric code, and then there's a proliferation of other codes and protocols that have emerged since. So one of the Toric code and the surface code, these are these rely on topologically ordered ground states in multi-qubit systems. So the surface code is a two-dimensional surface. The ground state, if you like, the logical qubits defined by Wilson lines moving across the lattice, and these are resilient to local errors. So up to some number of errors or qubit flips that aren't supposed to be there, one can actually recover the correct state of the logical qubit. So then there's been an enormous development of hardware and algorithms, and this is and there's just remarkable progress. But this is really at the interface of lattice spin systems and lattice field theories and quantum information science, quantum computing. And just to point you to one of many, many really interesting works, there's a PhD thesis from John Preskel's group, the ABCs of the color code. So this is a very nice thesis looking at topological quantum codes. And so the picture here that I also took from that thesis off on the right-hand side shows, you know, in a pictorial way what's going on is one is able to apply stabilizer codes to correct localized errors, for instance, in the blue region, but the logical qubits defined by what happens globally. And so there's been a significant, during the last 20 years, activity in numerical simulations, classical lattice simulations of spin systems, finite temperature systems, for instance, to understand the properties of surface codes and make efforts to do full simulations of logical qubit systems. There's a paper here from 2012 by Fowler, Mariantoni, Martinez, and Cleland, where they performed extensive numerical simulations of the surface code. And what's shown here on the left-hand side is the logical X error rate, P sub L, versus the per step error rate in the physical qubits. And so there's a threshold. So this is like a finite temperature field theory. It is a finite temperature field theory. So there's a threshold below which that as you increase the size of the system, the fidelity of the logical qubit improves. And above that threshold, it gets worse. And so you see these curves, even with for d equals 3, roughly it's a 1-to-1 scaling with 10 to the minus 4 physical rates per step. You're looking at a logical qubit error rate of 10 to the minus 5. Whereas you get up to 55, then you see rapidly one converges to a high fidelity qubit, logical qubit. And so there's certainly an optimization that goes on here. And one of the things that we realized just recently is that, you know, if you have an asymmetric distribution or a non-trivially distributed support in your logical qubit space, then you can work with some qubits that are that require high fidelity, where other logical qubits can be quite low fidelity. You don't have to have a system that's homogeneous. In fact, you can have heterogeneous distributed type of error correction. Yeah. So recently, it's been, results have appeared in the literature, particularly from Google and from Honeywell, for two instances where using a repetition code, Google's shown, in fact, you have exponential convergence as you increase the number of qubits in the logical error rate. So this is the logical qubit gets better exponentially as you add qubits to the system. So this is very encouraging, very much on the path towards a full implementation of a surface code. And similar types of progress have happened in other types of color codes as reported by Honeywell this year also. So even 2 years ago, we were not thinking that error correction is something that we would see anytime soon. And so we were somewhat resigned to working with quite noisy qubits, but I think we should be encouraged that it seems like we're kind of fast tracking on to having error corrected systems. Now, I'm hoping that doesn't conflict with what you were told earlier in the day. But, so on to nuclear physics now, and I want to talk about some of the systems that where quantum computing is expected to give us an advantage that's you know, on the prime objectives for nuclear physics research. One of these is in neutrinos, and the transport of entropy and flavor in neutrino physics. And so you can show that in these systems, these dense systems, for instance, in supernova, where the number of the neutrino density is high, then the interactions of neutrinos with themselves is actually the coherent interactions of neutrinos with themselves is important in how the flavor oscillates as they move through the system. So not only do they interact with the leptons and hadrons, they also interact with themselves. And so those interactions are highly non-trivial, and it's well understood the classical computing resources to do precision simulations of this is extensive beyond exascale. And so on the other hand, a quantum device with the system mapping onto spin systems, the quantum devices offer a potential opportunity to be able to make progress here. And so in fact, at lowest, if you're just looking at coherent neutrino interactions without the possibility of scattering and so forth, that type of forward scattering maps nicely onto a spin model, one spin and an interaction of two spins, similar to what we saw before. And so then there's been a number of studies that are looking at the behavior of these systems by a number of groups. The groups are listed here on the bottom left. And what's shown here on the bottom right is the half-chain entanglement entropy as a function of time after you turn on these interactions for beams, anti-parallel beams, as a function of vertically the difference in the beam energies. And so you see that in fact there's a region that the difference in beam energies makes a significant difference. The transformation's not smooth. There's a lot of interesting dynamics in the behavior of the entanglement entropy. So this is an area of exploration that's really just taking off now. And on the next slide, on this slide, you see some of the other results that have been obtained, both from classical computing. For instance, the bottom right is work looking at exact solutions of these systems with classical computing up to 9, and you see that there's non-trivial structure. And then the diagonal panels are the results obtained on quantum devices themselves. Now, so what you see is the challenges that we face in using quantum devices. It's one of the many challenges, but you see that the quantum results resemble, but they're not reproducing with high precision the results, except at a couple of values of parameters. So we're in a situation here where one's able to, in these complicated neutrino systems, use quantum devices to gain qualitative understanding of what one sees, what one can obtain from classical solution, but the precision's not there yet. But I mean, this is very exciting to actually be able to examine these systems. In the area of nuclear structure, there's been a number of computations, and this is something I'm really not going to dwell on much at all. But there's been computations on various devices, both trapped ion systems, IBM systems, and quantum frequency processors, optical systems, looking at small nuclei up to 4. And one's able to recover what one expects by, so basically sensible calculations yield sensible results. There's again some interesting features extracted with respect to the behavior of determining, for instance, ground state energies. There's some cancellations that one sees that one's going to have to deal with, but these seem to be under control at the moment. There's work projects at Livermore and Fermilab, but mainly for nuclear physics, it's the Livermore-Trento activity and looking at tensor forces between nucleons. Just so imagine you start with just 4 states and ask two nucleons and looking at the behavior of the spins as a function of time. Due to the tensor interaction, and this is non-trivial, this doesn't scale well on a classical computer, but in these simple systems, they're using microwave cavities with a transmon, and then performing large-scale classical simulations to figure out what is the signal to inject into these cavities. And the results are pretty impressive, both what's actually been accomplished to make this system work, and also the results themselves. And what you see here on this slide in the middle panel is you see that after performing, by injecting a long train of unitary operations into this cavity, one's able to recover the fundamental energy levels of the system, the energy differences between energy levels of the system with high precision. So what you see in this middle panel is a comparison of the exact solution to the system versus what's extracted through going into the frequency domain of a measured time sequence. So one's actually recovering what one expects to recover with precision. So it's a really nice result. There's been work by my student Anthony Charavella on looking at particle decays. So the question is, when you have a quantum real-time decays where you actually have a particle with some given width, then how do you measure its width? How do you measure its lifetime? So he did some work on that on IBM's devices. There's been work, Thomas Papenbrock and Gautam Rupak and others, on looking at the matrix elements of NPDD gamma, looking at this inelastic nuclear reaction as again a first step to going towards more complex systems, and they were able to recover well from the device the matrix elements. And then there's work by Alessandro Ruggiero and Joe Carlson and others looking at multi-nucleon systems. This is relevant in part for the DUNE project, neutrino experiment. And of the many things they've looked at, they were able to extract the 3 nucleon density on any particular lattice site and compare it with what they expect. And they find that once you've done error mitigation, in fact, you recover what you expect to recover. So now sort of some big picture items to consider. So in particular in the evolution of the hardware, so if you had a perfect machine, then life is easy, but of course these machines are not going to be perfect, and typically the physical qubits are going to be noisy, and even with Majorana qubits, if Microsoft can succeed and QSC can succeed, then these plots still exist. So this is taken from a figure by Google, and you see that on the horizontal axis you see the number of physical qubits, and on the vertical axis is the maximum error rate, and the NISQ error is this sort of gray cloud sitting here, and the representative hardware evolution is the dashed line. So at some point, once you cross the error correction threshold of this roughly 5 × 10⁻³ that I showed on that surface code plot, then it's just advantageous to not worry so much about the actual error rate in the physical qubit and just to add qubits. And so that's one possible trajectory to go forward as far as how the hardware might evolve. And so typically one will generate a multi-purpose machine, and it will sit on this curve, and then at some point you'll be able to do achieve objective A, and then achieve objective C, and then achieve objective B. And maybe you'll be able to do them all at once on one machine, or maybe you'll have to wait for a different generation and so on. However, there's opportunities then for going beyond commodity hardware as has been done in the past, and to design one's own hardware through a co-design process, so that it could be that objective A can be accomplished just as well with, say, 20 logical qubits, depending on the number of operations that you need to apply. And so typically there's always been advantages to developing hardware for specific tasks in order to make progress. And if you look at the evolution of classical computing, this is how things have proceeded. And again, one has this epsilon, this B piece in BQP to play with. So there's a certain tolerance that you need your computation to achieve, and you're free to distribute this error in the optimal way to actually accomplish the task. And it could be you might have slightly noisier hardware and slightly more gates to apply, and that's the most efficient way to go forward, or vice versa. So there's a whole design process that that has to happen, and is starting to happen, and has to happen to accomplish our scientific objectives. So let me start moving into quantum field theories now, a bit more deeply. So one expects that if we have n degrees of freedom interacting locally for some time period t, that we can simulate this with n degrees of freedom in our device by the application of t time steps for a total of nt operations. And it turns out that you can show that this is in fact the case. So it's polynomially scaling with n. And even for fermions, this has not changed. It still scales proportional to t, but there's some polynomial function of n. And it's also the case that, as you sort of intuitively expect, that d-dimensional systems are optimally simulated with d-dimensional simulators, or d-dimensional quantum devices. And I learned within the last 7 or 8 months that, in fact, this is how biological systems map their intrinsic systems, like nervous system, into the brain. The topology and is effectively the same as of the system itself. So you don't scramble a 3-dimensional system onto a 1-dimensional system, or vice versa. It's in fact most efficient to simulate a d-dimensional system with a d-dimensional system. And so this means that for us in nuclear physics, that in the future, to do 3-dimensional QCD efficiently, we're going to be looking at 3-dimensional simulators. It seems that's the only way that this will be done efficiently. So real-time evolution is something that's golden, in fact, as I mentioned many times, because it actually is something that quantum computers can do efficiently. It sits in BQP, and so not only can one perform time evolution of a system, if one needs to, say, prepare a state, and I'll give you an example of this in a little bit, if you can prepare a state in a sort of compact region and then use something that's equivalent to time evolution to actually make the true state that you're in search of, then that's something you can do efficiently. And so the way to move forward here, typically you have a Hamiltonian where various elements of the Hamiltonian don't commute with each other, but one can do a Trotter approximation where you just act with the e to the I, each of the different elements in the Hamiltonian for some small time period, and then just do that many times, and you can show that the error scales like of order t² divided by n. So as you take n to infinity, it converges to the answer that you're seeking. In present day hardware, unfortunately isn't that large, and so the Trotter errors are significant, and I'll show you examples of that. And when I say significant, it's of course always relative. And it's also the case then that the actual result up to some again, 1 over n error depends on the order of application of these infinitesimal elements. There's been extensive studies in various systems, and now moving into the lattice field theory systems, lattice Hamiltonian systems, of the behavior of trotter evolution. And it turns out that, as you'd expect, there is a time where if you go far enough, your errors catch up with you, and in fact, the system becomes chaotic. And there's a nice study here out of the Trento group, led by Philip Hauke, and also involved Peter Zoller, where they studied in this spin system what happens to your predicted time evolution, the final state after evolving, as you evolve for a certain period of time for a given fixed size of trotter decimation step. And sure enough, there's a point where you essentially lose control exponentially as you move into a chaotic phase. So again, for any realistic simulation, one has to understand what the objective is, what is the target, and this is going to then define the tuning or the size of the decimation for this particular method that you're going to have to use. There's, of course, you don't have to use trotter evolution. There's other variants on this. There's a number of other methods that have been created. They're all really quite beautiful. So one of them is linear combination of unitaries. And so one has then a quantum circuit of the form here where you introduce auxiliary qubits to control the operations you apply on the system that you're interested in. And so, for instance, I've just mapped out what happens, what the circuit does to some system initially in 0 and psi. And you can see at the end of applying the circuit, you have a linear combination of the auxiliary qubit being in 0 and the physical space being acted on with v plus u, and then with the auxiliary qubits in a 1, then it's in v minus u. And so then at that point, if you're interested in just keeping v plus u, you perform a measurement on the auxiliary qubit, keep the events where it's in 0 and throw away the events that it's in 1, and you've actually then accomplished evolving your state psi into a linear combination of the unitaries u and v. And of course, this then generalizes if you have 20 different unitary operators that you want to apply, then one has to apply this multiple times. Also, people have spent time and effort understanding the scaling, the asymptotic scaling of each of these algorithms. And so I just show you for trotter, randomized trotter, and then also this algorithm called Q-drift, which is statistical in nature. And understanding how these algorithms scale is important. You know, I mean, you might think that for a small system, you're doing quite well, but then eventually there's another algorithm that's going to be more efficient. We're still at the earliest stages now where we don't know the scaling of our systems, even for the small system, even for these small system size and intermediate sizes. We just don't know what that is yet. And so that's a program, in fact, that's underway to determine those things. So as an example, I'll show you some work that I was involved in with my students, Anthony Chavarella and Natalie Clough, who's now a postdoc at Caltech. So this is a small lattice QCD system for a one-plaquette system. The simplest thing you can imagine, you just have a loop of color flux traveling around, confined into the square. And then you can ask, if you initially prepare this in the state 0, what is the probability of remaining in 0 as a function of time, and then what is the time dependence of the electric energy in that plaquette. And so what you see, these are real results obtained on IBM devices. And one trotter step, one has good control of the statistical error bars, but the systematic error compared to the true curve, which is the black curve, it's not representative. And so then one can then shrink by a factor of 2 the size of the trotter step, and one does better systematically, but the statistical error bars have got a little bit larger. And so one can then go to 3 and 4 also. And you see that there's a trade-off here between the systematic error from the size of the errors that you've introduced deliberately in your trotter decimation versus the number of gates that you have to apply to the actual hardware and the errors that accumulate as a result of applying these gates. We also looked at Q-drift. So this is one of the statistical implementations of the time evolution. And in fact, while Q-drift performs very nicely asymptotically, better than Trotter in general, for the small systems that we have, it actually doesn't perform. It's not the preferred method, in fact. There's large statistical fluctuation that you see. So one has to perform very small steps and then very, very large sampling. So in general, what one has to do in a quantum field theory, one's going to define a lattice of fields. There's going to be the gauge fields on the links between the grid points, and then there's, say, fermions or scalar fields defined, or both defined on the grid points. Real-time Hamiltonian evolution. And so typically I've only mentioned so far Q bits, but one, of course, is free to use any finite discretized Hilbert space or continuous one if you control it. But typically one can think about Q bits, Q trits, or Q dits, and so forth. One has to define boundary conditions. One has to then define the degree of hybrid, how much classical, how much quantum, and so forth. One has to understand the problem to know the answer to those questions. And then there's going to be all sorts of error bars, all sorts of uncertainties here, systematic ones. One is from truncations of the field, and that's on top of the ones we know about, the finite lattice spacing, finite volume, the mistunings of the quark masses, and so forth. There's certainly going to be benefit to working in low energy spaces. We know this from effective field theory, and the lattice QCD is a low energy effective field theory solved numerically. On the quantum simulation, there's going to be analogous low energy effective Hamiltonians that are constructed, at least unless you're looking at high energy fragmentation, in which case you're going to have a lattice that encompasses all of those kinematics also. There's Gauss's law, which has to be implemented explicitly in the Hamiltonian formulation. And I'm going to say more about that in a little bit. But ultimately, there's a program that's just barely starting to determine how one goes about establishing a complete quantification of uncertainties in these Hamiltonian quantum simulations, in analogous to the ways that these are laid out in nuclear structure, reactions in astrophysics, and lattice QCD with classical computing. So I don't really need to say much more about this. I think this is already known. The seminal work in this area is by Jordan, Lee, and Prescott in a small number of papers where they showed that, as I mentioned last time, that scalar field theory sits in BQP, and the analysis is straightforward, but with many parts to it. The Hamiltonian that one starts with is shown here. It's very simple. It's a spatially discretized spatial gradient, a mass term, and then a lambda phi 4 interaction. There's been work also at some point after that work using continuous variable systems, and particularly optical systems, to simulate also lambda phi 4 theory. So there's an algorithm here to show you how to begin to separate, to use lasers and optical systems to simulate lambda phi 4 quantum field theories. So this is also really another really interesting avenue. So typically here with for the scalar field, which is obviously a continuous variable, and there's some in each point in space, there's some wave function. Then this is digitized and mapped onto a finite dimensional Hilbert space, say on using qubits or qdits. And so then really a three-dimensional system is really a four-dimensional system, because you have for each link you have now, sorry, for each site, in this case you have an n-qubit Hilbert space that's attached to it. So the work of Jordan Lee Prescott, they showed how, starting from non-interacting scalar field theory, how then you could create Gaussian wave packets that were well separated, and then perform a time evolution operator forwards and backwards in time to go from, to adiabatically go from the non-interacting theory to the fully interacting theory, and then release the wave packets. The wave packets then collide and produce the particles they're going to produce into the final state, and then how to measure those particles and extract physics and cross-sections and so forth, inelastic cross-sections. And they've provided error estimates, a complete tracking of the uncertainties, systematic uncertainties from beginning to end in this analysis. So this is complete, and it was this work that showed that in fact it sits in BQP. So this is the gold standard now, that for any other field theory, which are typically more complicated than this, but this complete analysis from beginning to end with the various decimations and discretizations, this is the objective. Let me skip that. Let me skip this also. So for scalar field theory, when you handed this finite dimensional Hilbert space, you're free to define the fields any way you want. You don't have to distribute the qubits in an organized way about each of the sites. You can just do a large uniform distribution and then define, for instance, hypercubes that define the field you're interested in, or you can localize all the qubits on one site and define the field wave function to reside locally. That's the one that's been studied and understood the best. But one can also then, even in one of those Hilbert spaces, you don't have to use the field basis. One can use, for instance, the harmonic oscillator basis. And so we did an analysis. We're looking at the Jordan-Lee-Preskel basis, which is shown as these upper elements in the table, where you can see very clearly the behavior of you truncate after two-body interactions. Whereas if you're using a harmonic oscillator, then typically you need all in-body interactions, which then become quite costly. And if you count the number of gates that you need, these entangling C0 gates, then with the JLP, with 6 qubits, you need 120, whereas with a harmonic oscillator, you need more than 1,000. So there's an efficiency here that the mappings, you have freedom with mappings, but that freedom comes with a cost. There's some that are better and some that are worse. So moving on to hardware. So this was put onto hardware, and there's some lessons learned here. This is work that Natalie and I did. So for instance, even a simple gate, if you look at the right panel and ask what do the gates do as a function of angle. So this is just a rotation. Then you see that the hardware responds differently depending on what the other qubits are doing. So if the qubits are all in the 0 state, then you get one performance, which we've called the vacuum. So the angle is actually slightly in the wrong place, but not by much. Whereas if all the other qubits are in a particular wave function, and we chose one in particular, then in fact, you actually get a different performance on the rotation on a particular qubit. So you're really dealing here with these quantum devices are quantum many-body systems themselves. There's a non-zero renormalization that happens through the communication fabric so that a one-body operator actually turns into applying an n-body operator. So there's a non-trivial sort of renormalization group flow that you have to keep in mind in going from the circuits that you want to apply to the actual circuits that you need to apply on the device itself. So this is what I was pointing at a little bit earlier. And this is it's Solmer inflation, where Rolando Solmer showed that if you want to initialize a Gaussian on some large chunk of your Hilbert space, you can actually initialize a Gaussian on a localized region and then use basically pseudo time evolution, unitary operations to evolve the Gaussian wave function just through free evolution of free field to the much larger one. And so you're utilizing the fact that this is a BQP process, the time evolution, and it allows you to while you have errors, the uncertainty, systematic errors are dictated by your initialization onto a small number of states, you can actually do that quite well. But then you save a lot by being able to just do a time evolution forward to stand up the same wave function, but on much bigger part of the Hilbert space. So that's really kind of very nice, very nice algorithm. I will skip that. I'm just checking time. Yeah. Okay. So I want to say some words about Yang-Mills and moving towards nuclear forces. So the basic framework that exists at the moment for Hamiltonian evolution was written down in the 1970s by Kogut and Susskind. Kogut, Susskind, Hamiltonian. It's written in terms of electric field operators squared and plaquette operators, the magnetic piece. There's a first implementation on hardware by Zohar, Sirac, and Resnick in 2013. And there was this really nice paper in 2006 by Burns and Yamamoto that just established the framework for issue 3 in a hypercubic lattice. So there's been many works. I'm not going to be able to talk about all of them by any means. And some of the early works on the Hamiltonian are shown here at the bottom. And so this is the second instances of I should have paid more attention in grad school. And this is Jorge's fault, actually, because Jorge, Martin Zernberg, and Steve Kuhnen wrote a paper in the late 1980s that is directly relevant for Hamiltonian simulation on quantum devices. They set up issue 2 lattice gauge theory and performed classical computations looking at how these systems evolve. How do you set up the wave functions and how do they evolve? So in fact, when I started thinking about this, I went back, I remembered this paper and I went back and I read it, and there's a lot of interesting things there. So again, things I should have paid more attention to. So for pure Yang-Mills, generically issue N, but issue 3 is what we're really focused on here. Then you can assign, we're just now talking about fields living on the links, forget about the quarks. Then there's an issue 3 irreducible representation, or a string of issue 3 irreducible representations that live on these links, and each of them has some amplitude. And so the wave function for this entire system is a coherent wave function with amplitudes for each of these irreps. And so if you look, you can collapse things again by gauge invariance, and you essentially don't have to worry about all of the different orientations of the irreps in each of the spaces. You can just work with the total dimensionality. And so one can set, one way to possibly map this is to have 2 registers of qubits, one that keeps track of the number of up indices and one that keeps track of the number of down indices on each of these tensors. And then there's some wave function. And so, for instance, in a 2-dimensional system, this is kind of the layout that one's working with. And the asking about the amount of electric, the electric energy is easy. It's just a diagonal operator. It just asks what is the expectation value of E squared, and working the electric basis, that's just a diagonal operation. On the other hand, the action of the magnetic operator changes the irreps. And so one has to understand then applying a plaquette operator, which is effectively applying a 3 on each of these links and a 3 bar on each of these links and averaging. One has to understand the action of that. And so the connectivity in color space is actually quite simple. So 3 cross a 3 gives a 6 and a 3 bar. So it only takes you to you go from the 3, the action of the plaquette operator takes you to 2 different irreps, and whereas if you act in with the box dagger, which is 3 cross 3 bar, then you have an 8 and a 1, takes you to another 2. So typically you're just connecting 1 to 4, and it's basically a honeycomb type configuration. And it was shown that calculating the SUN Clebsch-Gordons turns out to be BQP also. So this is something you can do efficiently on a quantum computer. That was shown by Bacon, Chang, Harrow in 2006. The deficit here, as I mentioned earlier, is that Gauss's law, conservation of color flux, needs to be enforced by hand. And so if there's an error in the system, which will typically take you from one color irrep to another color irrep, one has to then look for that and correct it if one can. So some equations which are look a little scary, but they're not that bad, is that you can go through analytically and compute classically strings of these coefficients that you need for the controlled operators. So what I mean by that is that the actual action of the plaquette operator on a given set of 4 links in a square depends on the flux that's actually coming in from the other legs. And so there's non-trivial differences in amplitudes that just have to be computed classically to know what operators you're going to apply quantum mechanically. I think I'll skip that because we're running out of time. You've already seen that. And you've seen that. Yeah, so just let me make a comment. Sorry. So just let me make a comment here that the amount of classical computing grows non-trivially. So if you want to look at the control operators and their amplitudes in such computations, then what's shown in this table is how things scale as you increase the dimensionality, the possible dimensionality of the color lengths. And so you see that, you know, starting with including a 1 and a 3, then you have 81 matrix elements and 81 physical states. Whereas now when you're up to including up to the 24 era, you have 24 million matrix elements and 2 million physical states. And this is not a large cutoff. So as you move towards the continuum limit and want to make comparisons and compare with the experiment, the dimensionality of the space grows and grows and grows. So the amount of classical computing power is going to grow too. Yeah, so one of the interesting things here is that, and I hadn't really appreciated this for a long time, and that is the potential for confinement and error correction. So one of the things that happens is if you have an error in an error correction code, then as you keep applying operations, it can drift around. And when you produce 2 of them, and they can drift around, and so you have an order volume challenge to find them and get rid of them. Whereas if you're working with a confining theory, then in fact you know that the charges will remain localized around each other. So you don't have a very large volume at all to have to search once you find one error, whereas the other error. And so what this means in simulation, for instance, if I look at the right panel, then if I have an error and I blow out this link, a cosmic ray comes through, puts error here or whatever the origin is, then I know that I'm going to have a color charge on one site and then a color charge on an adjacent site. And so this just looks like I put in external color charges, for instance, like quark and an anti-quark or something. And so we haven't really figured out yet how one can take advantage of this to dynamically or even minimally operationally remove errors in Yang-Mills simulations, but that's one of the things we're actually working on. And I should say there's really quite amazing papers from 2015 by Hector Bombin, and using confinement to reduce error correction, at least the overhead into a single shot. Okay. Yeah, so let me just sort of back out now to move towards concluding. So there's a lot of activity in the community. I mean, more activity than I can describe to you. And there's a lot of new ideas coming out, and particularly ideas for simulating both spin models and gauge theories. And so the University of Maryland has a strong effort, and they have significant experimental trapped ion systems, as you know, and they have strong theoretical efforts in quantum information and nuclear particle physics. And so these groups are working together. And so, for instance, there's a paper by Zora Davudi and Norbert Linke and Guido Pagano on implementing localized phonon dynamics of the atoms in the trap, now using that to encode gauge theories, the gauge fields. And so there's a very nice paper that shows how you would actually do this with local addressing. And similarly, that same group of people plus others showed how you would develop interactions and laser pulse sequences to implement a direct three-body interaction, which is, of course, important for effective field theories of multi-nucleon systems. Okay, so let me close. I want to say just one slide on the activity that we have in Seattle that we've just started. It's the incubator for quantum simulation. And we're really focused on a broad-based effort locally, research effort locally to advance quantum simulation for nuclear physics, quantum field theories, and generally the standard model, effective field theories. And so the things that I've talked about generally all are relevant for that, including understanding fundamentals and the formalism of entanglement all the way through to understanding how to run hardware. In addition to the local research activity, we run workshops. If you go to the website, we solicit proposals a couple of times a year. If you have interest in organizing a workshop or want to suggest a topic that you'd be interested in, please either submit a proposal or just send me an email. And typically the workshops will be a couple of weeks or a couple of days, depending on what's appropriate, to bring people together to really focus on the strategic projects and activities to move this area forward. And there's a workshop next week on scientific computing and simulation on near-term devices, focused on strongly correlated systems. And this is in coordination with the NQI Center, QSC, led out of Oak Ridge. Okay, so my last slide, I was going to write conclusions or closing, but really it's just the beginning. So I'd just like to say onward. And it's really, it's really fun and exciting to be in the second era of impact of quantum mechanics. So thank you very much.
Thank you very much, Martin. As you said, for some of us, these lectures were a fire hose of information, but we have them and appreciate it very much. So let me open the floor for some questions.
Stop sharing. Okay, good.
Maybe I could just unmute and ask.
What do you think?
So a very nice talk, and I get a sense of lots of. Is it fair to say sort of just test cases on sort of these proto quantum computers we have now for these algorithms or these approaches which have the potential to one day. I wonder if you had to make a guess as to where at some point, I think, because it's likely that fault-tolerant quantum computing may well be a long way off, but who knows?
Yeah.
But before that happens, will there be can you envision a moment where there's something that's calculated using a quantum computer, maybe just a small part, that could not be calculated classically? That's sort of a threshold moment that we talk about in condensed matter, where there's some nature paper where there's some correlation function in some model that you can say we couldn't have found this without a quantum computer. Is there some sort of near-term, quote unquote, near-term, and of course trying to predict that is foolish because it'll come from left field, but.
Well, I mean, it's a great question. And, in fact, there's a panel on next week's workshop to address exactly this, what is the low-hanging fruit for theory? And it's likely that digital computing will be the last arena where there's, and I don't say that it's not meant to be taken negatively, but digital quantum computing seems to be further out than performing simulations on an analog simulator that has impact experimentally. So for instance, you can have analog systems that are hundreds of qubits that you can act on in a controlled way. You can't do everything, but you can do certain things. So it's conceivable that looking for instance, for viscosities or some bulk behaviors of particular Hamiltonians that are close to the ones you want, which will give you quantitative insights that you can't get any other way, that you can't get it classically. So I suspect that's going to be, and this is just my own suspicion, that's going to be the path of first impact is that way. And it's probably not going to be a high precision number. It's going to be an insight how to adapt or improve existing calculations with a new piece of physics you identify with a quantum simulation. So that's how I think it's could play out.
I see. Thank you.
Do we have more questions? So Martin, here It's almost 5:30, so you're starting your day almost. Not quite, but so I don't know if there are other questions. In the meantime, if I can ask a question, I think early in your presentation, the day before, you mentioned, of course, Feynman saying that if you want to understand a quantum system, you should use the quantum simulations. So what is the status of this very famous sign problem that has making people very, very worried for decades and decades with classical devices in the arena of quantum computing?
Well, so yeah, so nominally, so in fact, you've had a very important question that's very pointed, because not all sign problems will be tackled and solved with a quantum computer. It depends where it sits. And so there are instances you can imagine where the quantum device will be able to solve the problem with a chemical potential that you can't do classically, but it's a problem dependent question. And in particular, when you have errors in the device errors, this can completely, well, I don't want to say that because it's not quantified, but one of the things actually really kind of at the front of my mind is, what are the limits of the systems where the quantum mechanics is hopefully going to get you around sign problems if you have an error and amplitudes no longer are canceling exactly. So it remains to be explored. So that's again something that's kind of front and center on understanding what we can actually hope to accomplish. And this is not just for nuclear physics. This is across the board.
Of course, condensed matter, of course.
Yeah, absolutely. Yeah.
Well, if there are more questions, please feel free to unmute yourselves and ask. And if not, then I'm going to thank Martin on behalf of the organizing committee and in general Florida State University for 2 great talks. And again, I wish you the best, the incubator, and all the best. And please send my very best to all my friends in Seattle. And then until next time. And again, thank you so much.
Well, thank you very much. It was wonderful. Thank you.
Take care, Martin. Bye-bye.
Bye.